Thank you so much, Yanni, and to QCware for having me here. Matt Langione from Boston Consulting Group, and just delighted to be at this first and still most important conference in the field. So I'm here to talk as much about generative AI as quantum computing, and really want to start with the value of generative AI for business, the roadblocks that prevent it from scaling for end users today, and then the convergence potential of quantum computing and generative AI. And that's not just quantum computing to address some of the roadblocks, but also how generative AI can accelerate the roadmap to quantum advantage, and of course the more visionary notion of convergence, where the two technologies work side by side and create kind of flywheel benefits with exponential power for users and for society. So there are probably very few people in this room, if any, that have not heard of generative AI. It burst onto the scene, at least in the public sphere, about a year ago and became instantly kind of the most viral technology of all time, reaching 1 million users in just 5 days. And bringing us kind of to the brink by some accounts of a very generalizable human level intelligence that you see with some of the scores on the right-hand side of this chart. For those of you that aren't as familiar with it or that haven't used it, I recommend that you do, to understand a little bit of what it can do. But let's take a look at what we did here. So you have on the left-hand side of the page Edvard Munch's The Scream, and I've just simply typed into the chat, what mood does the attached work of art convey, and what aesthetic choices has the artist made that contribute to the mood. And what it spits back in about 20 seconds is really quite remarkable. It breaks it down into kind of 5 aesthetic choices, from color palette to brushwork to perspective, where in fact, in perspective, it makes the interesting observation that the bridge is receding sort of sharply into the background, therefore amplifying the sense of depth and distance and making the central figure appear trapped or enclosed in the foreground. We're not going to fire the curator yet, but it is also worth noting that this is a pretty sophisticated insight, really at parity with what a lot of us are asked to do from a cognitive perspective in our day-to-day work. Now, of course, if the transformers and the architectures can do this kind of work, of course they can do more banal work. And it's also noted that as much as this is a kind of revolutionary history-making technology, where we're using it today and where it's creating value for end users are actually in some pretty operational efficiency kind of use cases. Think about things like document review and processing for legal departments, or front-ending call center work. This is a kind of a far cry from some of the heroic use cases that we imagine for the first generation of fault-tolerant quantum computers, things like materials design and drug discovery. That said, this kind of work is extraordinarily valuable to businesses, and therefore we think that within just a few years there'll be a $100 billion tech provider market for generative AI-related technologies, and really a factor of that in terms of value creation for businesses. So what can Gen AI do? Really, there are kind of 5 things. 1, it can understand unstructured, unlabeled inputs, as you saw with Munch's The Scream. It can extract knowledge, it can analyze, it can summarize, and generate. And the most important thing here are really these first 2, which together represent a semantic search, which goes beyond logic and beyond syntax, and actually intuits the semantic relatedness of concepts, and it allows us to really contextualize knowledge across modalities, not just text but image, sound, etc. And this is really kind of the source of its power. What's driven this is really more than anything model size, right? And so in 1 generation from GPT-3 to GPT-4, the advance in performance was that of a 10th percentile performance on the multi-state bar exam to a 90th percentile advance in the multi-state bar exam, and you see the order of magnitude in parameter increase as well. But what made this possible? How did models come to be so big? Really, there are three things here. One is algorithm advances. So we'll talk a little bit about the history of that, but one is an algorithm advance. And related to that, an exponential increase in the available valid training data that models could use. The third one is, of course, an exponential increase in compute power. So let's take them in order. There's a long history in machine learning that, of course, dates back to the 40s and cybernetics. But the annus mirabilis for the current paradigm with transformers comes in 2017 when Google researchers released a paper called "Attention is All You Need." And what attention refers to in this context is the attention mechanism that allows the model to understand context and salience in the absence of syntax and logic, right? And therefore, what it really enables is model access to unstructured data sets without human labeling. So we'll get to that now. So the issue with data here is that obviously, we're well aware that there's been this enormous exponential proliferation of data over the last 10 years, 10 to 120 exabytes. But you'll note that the fraction of that data, we understand where it comes from, our phones, social media, these sorts of things, that data was increasingly unstructured, right? And in a prior paradigm of AI, what would have been required is, human labeling at massive scale. What the attention mechanism enabled is labeling at machine scale, right? And so with the power of both structured and unstructured data, we were able to sort of harness the whole reservoir of available kind of human interactions. But of course, it does so with an attention mechanism that has quadratic time complexity. What that means is that to get more data into the model, you're going to need a whole lot more compute as well. And of course, no one in here is a stranger to the concept of Moore's law, but it is still remarkable to note that over the last 20 years, there's been a factor of 7,000 improvement in GPU performance. Okay, so these are sort of the drivers. These are well known. These are well understood. But what I think gets maybe less attention, too little attention, is the extent to which each of these enablers carries within it the seed of a challenge or a roadblock for scaling generative AI, right? So transformer models enable massive models to exist, right? But they're also greedy and inefficient. So we noted that we moved from the bottom 10% on the bar exam to the top 10% in one generation on GPT, but it also cost an order of magnitude to 1.7 trillion parameters and $1 billion in single run training costs. So that's one notion. The other idea is the idea of having enough data to feed the models, and we'll get into that in just a moment. And then the last one is just whether we have the actual compute resources to power the model. So the very things that give Gen AI its massive and transformational power are also challenges that businesses have right now in scaling and applying the technology. Let's take a look at the data problem. So the available internet training data could grow to another 2 magnitudes. Right now, GPT is trained on about 10 to the 12th tokens, right? And that actually already exhausts, some would say even more than exhausts, the available public data on the internet. With every order of magnitude increase, it reduces the normalized error rate by about 1/4 to 1/3. Right now, the normalized error rate's at about 20%. Human level's about 8 to 10%. So there's sort of 2 more orders of magnitude to get down to human level, which would reduce, the things that you've heard quite a lot about in terms of hallucination and other kinds of errors. The challenge, of course, is that, again, we've already run out of available data. And you may say, the standard objection here would be, well, but our phones and our computers, our voice calls, whatever else, are creating enormous amounts of data every day. So there's this proliferation that'll simply solve the problem. Maybe so, but that's where we get to kind of a quality objection, right? Where if you think about this first set of training data that went into the models, you had, Aristotle and Newton and Socrates. The next set will be like your text messages, YouTube and social media. So I think that there is a pretty significant, not insuperable, but significant data problem. The other thing to note is that there's this notion of compute itself. So if you think about it, this first, on the fastest super cluster today, you could train GPT with 175 billion parameters in 15 hours, GPT-4 in 60 days. And if we apply, very simply, the same scaling law, GPT-6, so another 100x increase, would take 16 years, or if you wanted to keep with 60 days, you'd need to parallelize 600,000 GPUs. And this comes, of course, at a time when wafer production is about 10,000 a month, and it takes even the lucky few that can get access to GPUs about 6-month lead times. So there are serious challenges. This doesn't mean by any stretch of the imagination that we're not extremely excited about generative AI. But what it does mean is that there are real roadblocks that require addressing. So where does quantum computing play in all this, and what's the story around convergence? So quantum computing, there's sort of three ways that I want to tackle this. One, the roadblocks that we just discussed. How can quantum computing help to alleviate those challenges? The second one is very much the reverse. To what extent can Gen AI be deployed to address some of the canonical challenges in quantum computing? And lastly, how, and this is the more visionary notion of how quantum computers and Gen AI can work side by side to create exponential benefits for users, for society. So the first one to note is just, of course, these roadblocks, where the transformer models are greedy. Kind of the golden goose here would be to use, whether on quantum hardware or quantum inspired on classical hardware, to actually reduce the size of the model or the fundamental architecture, the benefits of which would flow downstream. And there's already some research here. Quantinuum and CQC is researching natural language processing to reduce the size of neural networks themselves. So that's sort of one research vector. Another one, we had talked about the data problem. Many people moot synthetic data as the problem, as the resolution to the problem of data. But the issue is that synthetic data on classical computers lacks the intrinsic randomness, so that the discriminator module in say, a generative adversarial network can actually tell the difference, and therefore it removes or reduces its utility. Already IonQ is working with FCAT using quantum synthetic data in real-world use cases. So we think that that's an interesting vector. And then the last one is the compute resources notion, and this is in some ways the most ambitious potential convergence here. And in this case, you would run a model, for example, on a quantum machine. Now, of course, that's going to supervene on or leverage the first two kinds of roadblocks that I described, because of course the transformer model itself would be extremely inefficient on a quantum computer. But already, Zapata and others are doing research around substituting parts of MOLGAN with VQCs to produce the quantum GANs that surpass classical in performance. So these are early stages yet, but really, really important research areas to pursue, because the benefits are not just massive, they're also concrete and deeply felt by enterprises and tech providers in classical computing. There's also this notion of Gen AI accelerating quantum computing. And on that one, whereas in the previous, with quantum computing accelerating Gen AI, those were sort of speculative use cases. This one is not, and this is very concrete. Just yesterday at IBM's Quantum Summit, they announced that they're introducing a generative AI code assist for Qiskit that really would democratize access and allow you to program in Qiskit in plain language. And already in their transpiler, they're using generative AI, and apparently early results suggest 20 to 50% improvements in efficiency. These are really important things. But I think that another piece of work is to think about a future in which transformative changes to things like error correction and base algorithms could be tackled with generative AI. It seems absurd when you use the technology now. In some ways, what it's doing is predicting the next likely word. So how could it create an innovative breakthrough, in one of the most mystifying fields in the sciences? That said, the Chinese Academy of Sciences has a QEC GPT project that's actually doing the same and kind of innovating in this space already. Results are, of course, still very early, but it's promising to see that these technologies, that the Gen AI technology in particular, is being used to think through how to advance the quantum roadmap. So when we think about convergence, we don't often think about the roadmap kind of use cases that I just mentioned. What we think about is something much more like what we have here. Say this, a drug discovery workflow where two technologies are working side by side. Today, we have about 10,000 approved medicines, which is just a tiny fragment of the potential on the right-hand side, 50 orders of magnitude less than the entire searchable chemical space. And this is often mooted. The delta between the left-hand side of this page and the right-hand side of this page is very motivating for quantum computing research. But it's worth noting that it's not as though a quantum computer could simply simulate all of the entirety of chemical space and magically pull out valid drug possibilities. It's still going to be hypothesis-generated work. And that's where we see generative AI, which could intervene and actually exponentiate hypothesis creation. So potential chemical formulas could be produced that then the quantum computer would verify, on the atomic scale, on the quantum scale, the exact properties necessary in order to get to approved medicines. And so this would not only exponentiate the solving of the hypothesis, but exponentiate the hypothesis generation itself. And it's that double exponential that the likes of Satya Nadella has in mind when he talks about a goal of compressing 250 years of chemistry into the next 25. And I want to conclude my talk by saying that it's critical to start now. Because in the early days of traditional computing, nobody waited for error correction, and it's a good thing that they didn't. If you think about what landmark use cases there were for traditional computers in the 20th century, many of them preceded error correction. If you think about it, classical computers were used to unscramble Nazi codes, to simulate atomic reactions for the Manhattan Project, all before, in 1950, Richard Hamming got, frustrated enough to start developing the early error correction codes during his coffee breaks at Bell Labs. Now, the early stages of computing are also not heroic examples of go-it-alone tech providers. The real breakthroughs came with deep public-private collaborations, the likes of which you see here with Harvard Mark, which was funded by the Navy and was developed side by side with US Army Corps of Engineers, delivering specifications for what they needed. And on the right, UNIVAC, which was Remington Rand, but also funded by the Census Bureau, which wasn't a passive customer, instead was working alongside researchers for 6 months on the design. And the classic story here is that CBS was really the most famous company associated with this and really the first user in a sense. In 1951 on election night, UNIVAC had kind of a debut where it was going to come and predict the results of the election. And the Gallup polls had a 51-49 split, so they thought it was going to be a bit of a nail-biter. When 5.5% of the vote was in, UNIVAC predicted a landslide victory for Eisenhower. And the broadcast team suppressed the results and told the world that the machine wasn't working. And by the end of the night, it turns out that UNIVAC predicted the result within 4 electoral votes. And to their credit, the broadcast team came back on and admitted what had happened. And then the next day, in a legendary newspaper headline, it read, "Machine makes monkey out of man." But more than just a colorful anecdote, I think that this is actually a really important point about collaboration. CBS didn't actually pay for the machine, but they dedicated researchers. They sat side by side, made goals and specifications for the machine, And ultimately, it had an enormous kind of media following after the election night. And you see that the customers on the right came and were involved as well and became customers of Remington Rand. A lot of the components are in place today. I've mentioned the research at the Chinese Academy of Sciences. There's work with Toronto, Zapata, and Silico at the convergence of generative AI and quantum. IBM and Moderna are working to accelerate drug discovery, both with a generative AI perspective, with a quantum perspective, and at the convergence. And then governments have pledged $55 billion for quantum computing. But what's really important when you have technologies this complex and when you have a convergence this ambitious is to really unify these efforts at the scale we saw in the first generation of classical computing. I think that we can take a page from history. It's important and critical that we do so. Thank you so much.